fine for it to be.
Yeah. Okay. All right. So after the general introductions, the Parton model was a quick review. I assume you've seen that before. If not, let me know. Then we can quickly go over in tutorials. What I'd like to do now is another topic for tutorials, by the way, is group theory. I assume you've seen some of it, there will be a section in the notes that you'll get, a bit of an appendix on group theory, which if you have never seen it, you can study it this evening and learn it in one evening. But if you've seen it, we will not use too much group theory, but I'll assume you've seen that before. So let me begin by discussing gauge theory in general. Oh, that is really nicely visible. Very good. I can even write smaller. Now, to start introducing gauge theory, let's consider first a field theory for a complex field psi of x. So psi of x is complex. And field equations will describe how it evolves. For time evolution, typically, is invariant under change of phase. So under psi of x goes to e to the I psi of x. So just change the phase of the field, and it shouldn't matter for time evolution of the field, for the dynamics of the field, no matter what the theory is. In quantum mechanics, this is also well known, of course. The only physics is in the absolute value squared of the field, so the phase doesn't matter. It also means that if you, say, fix the field at a certain initial time t, and you do time evolution, that phase changes, only the phase shifts, the phase differences between two components of the field matters, not the absolute phase. So this statement has this meaning that there's a degeneracy in the degrees of freedom, in DOF, degrees of freedom. If the psi of x or any phase times psi of x has the same physics, that just means that it's degeneracy. And that's then typically a symmetry of your field theory. But now let's suppose we demand something stronger. Suppose we insist that the following change, so the transformation of psi of x with a different phase at every space-time point is a symmetry. So notice now that the parameter psi of x is a function of space-time. That's a much stronger demand if the theory is supposed to be invariant under local phase transformations. That's a much stronger demand on the theory. This is called rigid invariance, and this is local invariance, local symmetry, because the parameter here depends on x and there it doesn't. And this meaning is that actually if it doesn't matter that you change by phase, you can actually remove a whole degree of freedom, or maybe more degrees of freedom. So this in fact means that certain degrees of freedom are absent, meaning that they will occur, they seem to be there, and you write down the formulas for your theory. But if you really start counting at the end, there will be less than there seem to be, because of this strong invariance. For those of you who know electrodynamics already, you describe a photon field by 4 components, but only 2 are physical. So there will be a need for this kind of description where you have a field with a symmetry, meaning the Lagrangian is invariant under such changes. And we need to build such a theory, and that's what a gauge theory is. We should also need, see if I can go here if the camera follows. The light, is there a light here for this one too? Okay, it can still be vanity, right? So shall need a field to carry info, to carry phase info from one between space-time points. So if you change the field here, the phase here or there must be some field that knows about those two changes between space-time points. And that will be the gauge field. We'll see it appear. Now, why would you want to do this at all? So, why such a construction? Well, a couple of reasons. First of all, locality. It turns out that if you have fewer degrees of freedom physically than typically Lorentz covariant fields contain, you can, of course, pick the right ones, but that leaves you with a non-local theory with things like 1 over derivative in the theory. That's very difficult to work with. So if you want a local theory, you often do it in this way. We have a field with a local symmetry. Related is also Lorentz invariance. In this way, you can construct Lorentz invariant theories with theories that have fewer degrees of freedom than they appear. And also, this gauge field is often called a mu. The vector potential from electrodynamics, right? You know all this probably. The thing I always learned in electrodynamics is that this is not really the field. It's from this you derive the B field, and the so you've seen this, right? B field is the curl of the vector part of this, and the electric field is the gradient of the zero part. But the real physics is here. That's not always true. It's largely true, but in the Aharonov-Bohm effect, if you've seen it there, actually the B field is zero, but the A field is real. It changes the phase if you go left or right around a loop. So around the long cylinder, current cylinder. So so the A field is in some sense real. Confer Aharonov-Bohm. So here are good reasons, and the A field follows from this condition. So these are 3 reasons why you'd like to have a structure like this. So let's start with a U1 gauge theory. And the name, let's see if I'm followed. Very good. U1 gauge theory. This is really nice, luxurious. U1 gauge theory. U1 is the group of phases. Who knows the notation U1? Who doesn't know the notation U1? It's known to everyone? Yeah? It's just a group theory language of them. This is for U also an abelian group. So if you have G1 and G2 are elements of U1, then G1, G2 is G2, G1. That goes for all elements of the group, and that means it's abelian. If it's not true, then it's non-abelian. So let's start with a Lagrangian for the psi field. And the Lagrangian psi field is minus. The conventions, by the way, I'm using are perhaps not the ones that you know. It's minus plus plus plus. That will be in the notes. The propagators will be 1 over k squared plus m squared. But these are minor details. In the test, you will not be graded on that. So it's the notation that we use in the forthcoming book. And psi bar is defined as I psi dagger gamma 0. To see your knowledge, if the metric is minus plus plus plus, is gamma 0 Hermitian or anti-Hermitian? Anti-Hermitian then, right? Yeah, very good. So this Lagrangian, as it stands, has a rigid invariance. Namely, if I change psi to psi prime is e to the I psi. I drop the x dependence. It's by inspection. You see it's invariant, right? Psi goes like this, psi bar, because of the dagger, transformed to e to the minus I psi x. So it's obviously invariant. Right? So it's rigidly invariant. Let me actually change this to q times psi, where q is just the strength. Q is the strength, later will be the charge, just to acknowledge the fact that if we would have, say, two psi fields, psi1 and psi2, one transforms e to the I psi, the other one e to the 2 I psi, just to see that maybe some fields transform faster than others. So there's a Q here. Now, let's check for local invariance, the one we really like. Well, this one's easy, right? Psi prime e to the I psi x of psi, where again I have suppressed the x dependence here. But the d mu that sits in here, you all know the d slash notation. Right? You do, okay. The d mu of psi of x, that goes to well, e to the I, so with the q again. Q psi x d mu of x. That's fine. That would be as we like it. But this thing is changing, so the d mu can also act on the phase. So there's a second term. IQ d mu acting on psi. Psi of x. This one there if psi is a constant. So this is the one that's troubled. So this means that this action, this Lagrangian, is not invariant on the local invariance because of this term. Right, you see this? Because if I change the field, so this term is still invariant, right? It doesn't matter if the phase is local or global, but it's a derivative in here that causes the problem. No, this one still transforms with a minus IQ psi, but it's a derivative. So this term is left over after you do the transformation. So how to fix this? And this will, the answer to this will characterize the way that we approach this issue. And just basically improving the tools, the things with which we build Lagrangians. So if you realize that the problem is a derivative, the answer is, well, make a better derivative. So the answer is find a better, actually we will call it covariant derivative. And better would mean that, let's call this thing big D on psi, if this transforms as e to the I q psi of x d mu psi of x. So it would transform just like psi itself does. So in that case, we would have that that L is minus psi big D slash psi minus m psi bar psi is invariant. Locally invariant. Right? Is that clear? I still haven't told you how to do this, but if I can do it, it'll work. Right? So the question is now shifted, can I make a derivative that behaves like this? rather than like this. And the answer is yes, you can do it. So to do that, use the a mu field. So define d mu psi as, first it starts with a regular derivative, and then minus iq a mu of x acting on psi. So there's a second term here now to the derivative with this new gauge field inside. As I now make a transformation, I know what this thing does. It does that together with that bad term. This must also now transform, and it will transform such as to cancel this problem. So if we have if a mu of x, if this is the rule together to be used together with this rule for psi, changes into a mu prime, which is a mu of x plus d mu psi, then it's okay. You can sort of see it. If you wish, you can work it out for yourself. It's this second term in the derivative that cancels this particular problem. Right, so this combination, this covariant derivative, transforms like this. And if we can find such a covariant derivative, we have immediately a locally invariant action. So I can write this out also as the original term. Notice I've kept the symmetry as more important than the action. I will like the symmetry. I'm prepared to change the Lagrangian in order to maintain the symmetry. So if I write this out, I get the original one plus iq a mu psi bar gamma mu psi. If I just write out the derivative there. So this is an interaction. This is a photon-electron interaction, or in other words, force. So we've seen here that symmetry leads to force. One of these beautiful concepts in our field. Yeah.
What you said about action, you have to set the line about action.
So the original action, the Lagrangian, was here. I want to keep it locally invariant. Well, this is not locally invariant. It's more important to me that the action is locally invariant than that this stays Lagrangian. So I've changed the d to this d. That means I've added a term to the Lagrangian effectively, but now it is locally symmetric. Is that clear? So by demanding the symmetry, I've created the force. So this is a very important derivative, the covariant derivative. It's called covariant because this is also at x. The transformation happens at exactly the space-time point x, as opposed to here, where there's a derivative involved, and it always involves differences of space-time points. So covariant means it happens at the space-time point.
So usually a force has a space dependence, right?
Yes.
Can the symmetry term lead to a force, the distance dependence?
Well, that only happens with quantum effects when the screening starts happening. So that's at the quantum level. At this stage, it's all classic charge is a charge, and you just get classical electrodynamics out of this. So in that sense, this is just at the moment classical electrodynamics.
Even a Coulomb force has a space dependence, right?
The strong forces.
The Coulomb force.
The Coulomb forces.
Has a space dependence. 1 over 4 pi r.
Yeah, it's like classical electrodynamics. So that follows from here. That is just indeed what's in here. So it exactly follows from that principle. So it's an important derivative. So let's look at a few of the properties. And one thing that's actually an interesting one is the Leibniz rule. That means that the covariant derivative on, say, two fields, psi1 and psi2, is covariant derivative on psi1 times psi2 plus psi1 covariant derivative on psi2. that's maybe also something to, if you don't see this, it's also not, it takes three lines. Suppose that this one changes, psi1 changes with e to the I. Q1, psi1 and psi2 go e to the I Q2, psi2. So we have two fields psi now with two different strengths, and you can show by these rules that this is obeyed. And you have to look a little bit what that means, particularly what comes here. But it's a nice property of a derivative to have. Another one is that the commutator of two of these covariant derivatives acting on epsilon psi is minus iq d mu a nu minus d nu a mu on psi, which is nothing but minus iq times the field strength tensor acting on psi. Have you seen this before? Yeah. This is, so the commutator of covariant derivatives gives you the field strength tensor. By the way, so the nice thing is, it looks like you have two derivatives acting on this, but in the end, what you get is a function multiplying it. And you can sort of see why. But if you just act through that, all these things acting on psi cancel each other. Now, in this field strength tensor, we can derive its transformation rule from that, from A, and this is actually quite nice. This thing goes over into f mu nu prime, which is f mu nu. The thing is invariant, which is immediately obvious if you change A by a derivative. Here it is. That cancels out. So the field strength tensor is actually invariant. A final property, this is also, by the way, called some is calling gravity the Ricci identity. Also important is the identity associated with associative property, the Jacobi identity. Which is if you take a commutator of the commutator, so you would get d mu commutator with d nu d rho acting on psi plus cyclic. There's two cyclic terms. And that is 0 just because of the, if you write it all out, all the terms cancel. There's nothing particularly deep here. And from this follows d mu, something called the Bianchi identity. And for those of you with a bit more mathematical inclination, these are has some topological properties too. This is the Bianchi identity. So you see more or less, so every time such a commutator gives a field strength, and then you commute with this covariant derivative. And in fact, because this is invariant, the charge is 0. The covariant derivative acting on f is nothing but the regular derivative. You see here, there is a term, an extra term beyond the regular derivative, if q is non-zero. If q is 0, if the thing were invariant, this thing is absent, and the covariant derivative is the regular derivative. So the second term in the covariant derivative depends on how the field transforms. If it doesn't transform, it's not there. That's why we have normal derivatives there. And I can rewrite this in a nice, clever way. D nu f rho sigma is 0. That's a nice form of the Bianchi. So We have now constructed, we've struggled with, we defined local symmetry, fields, and how they transform. We constructed the covariant derivative. So we can now construct the Lagrangian, the full Lagrangian, for both the psi and the A field. If we also define the A part of Lagrangian as minus a quarter, and that is from convention F mu nu, F mu nu. This is clearly invariant under local symmetry because F itself is invariant. Then LQED is nothing but L psi plus LA. And so that's just minus psi d slash psi minus m psi bar psi minus a quarter F mu nu, F mu nu. So all of this simple Lagrangian explains all of electrodynamics, all of chemistry, all of atomic physics, etc. So it also shows that just knowing Lagrangian is not nearly enough. There are some of the people say, well, you know the QCD Lagrangian, why bother? Well, we know the QED Lagrangian, but there are whole fields that depend on how it works out in nature. So we've constructed that now, all from the covariant derivative here, and also the F mu nu was really out of the commutator of two covariant derivatives. Right, so this is the construction of non-abelian gauge theory. The thing you've learned now also is to solve the problem. Suppose I've used here a fermion field, psi. Suppose I give you a complex scalar field. Let's do a little test already. L phi is minus d mu phi star d mu phi minus m squared phi star phi. This is a complex scalar field, right? Lagrangian for a free complex scalar field. It is not invariant under local symmetry. Under phi goes to E, I, Q. This is not invariant. How do you make it invariant? Sorry? Just make this a covariant. Just change the font on the D and add the F mu nu squared. That's all you have to do, and then you're done. You also see right away from that, just because of two derivatives, that you will get an AA phi phi term in contrast to electrodynamics. So also here d mu. So this is a great tool, the covariant derivative, for making things locally symmetric. Let me also discuss a bit the field equations. For this theory. Now, you know how to do it from the Euler-Lagrange principle, I presume. You make variations of the fields, variations must vanish at the boundary. And then you have, I'll just give you the answer, d mu is I, Q, psi bar, gamma mu, psi, and I call this J mu, and this is the Maxwell equation, the inhomogeneous Maxwell equations. And there's also the one for the fermion field, d slash plus m psi is I, Q, a slash psi. So these are field equations. In principle, that's what they are. You can recognize this as Maxwell. This is the Dirac equation with a source term in some sense, but that's not so much what I want to discuss. I'd like to discuss this term here a bit. This J mu. That J mu is, how would you call it? A current. Very good. It is elementary current. It's a flying electron, and it has an attachment point with an index mu for a photon. So the photon can test the flying electron. Now, so this is indeed a current. So it's interesting to look at current conservation. So it is already true. It is true that d mu j mu is 0. This is right away true. Okay? Do you see why? From this field equation? There's antisymmetry, right? Just if the left-hand side with 0 right away. So this means it's a conserved current. You can also use, so this is one proof, also by if I just use this, suppose I didn't see that, and I just took this definition and started working there, then I could write this as IQ psi bar d slash psi plus IQ psi bar d slash acting to the left psi. Turns out that it cancels and is also 0. So this is 0 after using field equations. So this current is conserved after using the field equations. And it's important. Why am I stressing this point? Well, as I told you, this is where a photon can attach. And photons must couple to conserved currents. The reason they must photons must couple to conserved currents the reason is we have this, I'll just say it in words. The photon field A mu has 4 components, 2 of which are superfluous. We only have a massless photon can either have the spin this way or this way, so there's only 2 degrees of freedom. So this local symmetry essentially ensures that we can describe 2 degrees of freedom with a symbol, with a field that has that is covariant in 4 indices. So A mu is a covariant field, has a mu index, and still with that basic thing that transforms so nicely on the Lorentz transformations, just like any vector, we can describe it for with 2 degrees of freedom, thanks to this local invariance. But if the photon would couple to non-conserved currents, those unwanted degrees of freedom would reappear. You can more or less see this. Suppose you have A mu, J mu in your Lagrangian. And suppose I look at the non-physical part of this. And that is the derivative of some parameter psi coupling to J mu. This is the gauge part of that. Right. Now by partial integration, I can bring it to the other side. And then I would have this non-physical bit coupling to d mu j mu. And if that's not 0, it's there. So it better not be 0. So that's why the current must be conserved. Okay? So that's an important thing. Now, at the same time, this is a bit of a abstract statement. And what does it really mean when you work with QED? How can we constantly losing my brush? Here it is. So let's consider the impact of current conservation on invariant amplitudes. And invariant amplitudes is the name we give also to scattering amplitudes. So I'll write this underneath. This is equivalent. So when we do, this is QED at the Lagrangian level, but we may want to do QED collisions. And how does this somewhat formal statement of current conservation appear inside the scattering amplitude? Well, let's see. So let's imagine we have a scattering amplitude indicated by a blob. There will be lots of blobs in this course. And here's, for example, a photon coming in with momentum k and index mu. And there will be a number of other particles coming in or coming out, let's say. I just want to look particularly at the external photon where the momentum is k. So the invariant amplitude of the scattering amplitude m of k is epsilon mu of k. I can write it in this form, k. I should also write here dots. The dots stand for the other external momenta. And here I've written for the external photon the polarization vector of that photon. Is this something that is familiar to you? Who hasn't seen this before? Don't be afraid, you may not have had this. Well, that is really, so we should maybe do a little bit of repair on that in the tutorial sections to have incoming and outgoing photons, incoming and outgoing electrons. I'll just tell you what it is at the moment. So in diagrams, for an external line, for a scattering line, there is no propagator. Propagators only go from here to there over finite distance. These external lines go to infinite distance. Either they come in or they go out. So the propagators are removed. And but if you have, suppose this photon comes from some fermion line there is a mu index open. And what you can track with that gamma mu that sits there? Well, not the delta mu propagator, but you must specify. It's a photon whose propagator is removed, but you must specify its polarization. Is it like this, is it circular, etc.? And that's defined by this. It's the polarization vector of the external photon. You can think also of the photon field to be Fourier decomposition of, say, epsilon mu of k e to the minus I k dot x plus Hermitian conjugate. So it's basically the momentum decomposition of the photon. This is the momentum wave function of the photon. Where this photon is on shell, so k squared is 0. That means that k0, the zeroth component, is plus or minus the absolute value of the spacelength part. Right, it's on shell. Yes. Yeah. K0 is plus or minus. Shall I rewrite this, or is this? Just say yes. Yeah. So we have that k0 is plus or minus the absolute value of k. That's what k squared is 0 means. So we have here this external photon, and with again characterized by this epsilon mu, which can be in principle an arbitrary vector in any of 4 directions, or linear combination of 4 directions. It's momentum space after all. But only 2 are physically relevant, as I told you before. So how do you remove the unphysical degree of freedom there, just like we did in coordinate space here? Well, it's really quite straightforward to translate. So if you have the gauge variation of a photon field in momentum space, what does that look like? If you know that in coordinate space, I'll write it here, delta A mu in coordinate space is d mu psi of x. What does it look like in momentum space? So, Fourier transform, right? So it will be just minus I k mu psi of k. So if I would like that this particular mode of the photon does not couple to the process, so if I choose the polarization vector proportional to k mu, it should give 0. Because anything, if this polarization vector is proportional to k mu, it is proportional to the gauge degree of freedom, the unphysical degree of freedom, and that better gives 0. So that implies that we need, where did I write it? K mu, that's too low. Let me do it here. So we need that k mu m mu of k is 0. Right? So that is the equivalent of the d mu j mu is 0 condition, but now in momentum space for scattering amplitudes. So this is a more general form of d mu j mu is 0. For those of you who had a bit more field theory, and let me make a parenthetical remark, but for those who have not, ignore it. The way you can see this is, suppose you have the scattering amplitude as a correlator of gauge fields operators, and if you stick inside here d mu j mu is 0, d mu j mu, which is 0, and you do this in momentum space, you get exactly this thing. The correlator creates the scattering amplitude, and the d mu becomes k mu, and that's how you go from this operator equation to this relation on functions. If you have not seen this, it doesn't matter. In the notes, I will explain how this corresponds also to having only 2 physical degrees of freedom, and how this also helps in maintaining Lorentz invariance for having such an external photon. This may be a bit surprising. Let me at least give you the setup. So the Lorentz invariance issue. So I have a photon, 2 degrees of freedom, helicity plus or helicity minus. But I have 4 field components, A mu. How can we go from 4 down to 2? Well, so I can have the polarization vector of the photon in generally is epsilon mu, and I can choose any of 4 directions in the first place. It's a 4-dimensional space. I can take a linear combination of 4 directions, and I need to go from 4 down to 2. So the first one, I need to think of 2 conditions. This is one condition, that's the dot product of k mu with the epsilon mu of that same k is 0, so it's transverse. This is one equation, so now we're down from 4 to 3. Okay. This is transverse. And the second one is epsilon 0 of k is 0. You can choose that. And that's now we're down to 2. But notice now we have a Lorentz invariance issue. We didn't have it here because this is a Lorentz invariant condition, but this is certainly something that is not Lorentz invariant. So what current conservation also shows is that if I have this equation, or actually I have this amplitude, and I switch to a new Lorentz frame, then current conservation ensures that in the new Lorentz frame, all I have to do is put primes here, and I don't have to worry about anything else. So the whole thing still looks as the same expression in the new momentum frame, in spite of the fact that I have this condition, which does not look Lorentz invariant. So we can discuss it in the tutorial, and it shows the importance of currents conservation. It saves Lorentz invariance. Now, as the last part of abelian theory, I'd like to discuss something also related to scattering, amplitudes, and charge conservation. Usually, if you had field theory and you've had the issue of charge conservation, it usually is discussed in terms of this condition. Usually you get that the charge is equal to the space integral of J0, right? We won't do that, right? We'll show it a different way. It's still true, but I just want to use a different language. Let's do it here. It also goes, the reason I also show it is it shows the power of a diagrammatic analysis and thinking about diagrams in a more general term. It also is the first time in sense that the so-called iconal approximation comes in. So this form of charge conservation you may well not have seen before. So let's see how we do. Conserved charges. So consider a blob again. So here we have a blob. Here's a photon. The charge flow index mu, here goes the photon momentum k, and a charged particle, let's say a scalar particle, comes in and with p prime and with p and goes out with p prime. The blob just masks a lot of diagrams that could be there, loops, tree level, whatever, but all I know is charged scalar comes in, a photon comes in, out goes the charged scalar with momentum p prime. That's all I define. So this is, represents in some sense a scattering amplitude, an invariant amplitude. And we have, of course, that k is equal to p prime minus p, my momentum conservation. Now I can say something very general about this amplitude without knowing what the diagrams are inside. So I can say that mu depends only on p and p prime. And why is that? Why doesn't it depend on k? Yeah, it's dependent momentum, right? So if I know p and p prime, I know what k is. And the mu index here is this dangling index that hangs there. And well, it's a vector, obviously. So what kind of vectors can I make? Mu is a single index, so it's a vector. I can write it as the sum of p and p prime, and let me times some scalar function, which can depend on k squared, p squared, and p prime squared. That's one way I can make a vector. There's a second way I can make a vector. P prime minus p. That's the G mu is 2 indices, and that only helps you raising and lower. It doesn't really help. But you're right. So this is, and p prime minus p is k. So I can just write here plus k mu f2, and use momenta again. And these f's are typically called form factors. They just encode our ignorance, but at least the vector structure has been already removed because we can know what that is. We also assume that this particle is the same as that particle. So we assume that p prime squared, p squared is equal to p prime squared is equal to minus m squared. This is the minus because of my convention. Sorry? Yeah, so these two are on shell. But no, there's not a 3-point interaction. Only 2 of the 3 can be on shell. The photon is not on shell then. Now, but this is of course a case of what we just discussed, and it must be 0. So let's see what that implies.
But if you take p and p prime is not on shell, then is that implied?
No, for this to hold, the other external particles in the amp is a good question. The other external must be on their mass shell, otherwise it does not hold. That's a general statement. Other photons you do not have to. All external charge particles must be on their mass shell, otherwise it does not hold. Yeah. That's basically because the field equations must hold, as I discussed earlier. The field
terms arises in that.
Sorry?
Coupling terms in arises. If they are not on shell, P and P prime, then this identity should be.
Then that's not zero. Yeah. But we do assume it's on shell, so this is 0, but this is also equal to pre prime squared minus p squared f1 plus k squared f2. I've used here that k is p prime minus p, so you get this difference. But this is 0. So this means that f2 is 0. f2 of k squared minus m squared is 0. Yeah, that's f2 is 0. Oh, this is just the two. I can make only two possible vector structures with two momenta. And by current conservation, I've shown that one is 0, leaving only one of them. And so what is f1? Is f2 is 0. What is f1 then? Well, f1 is the charge form factor. FF, the form factor. Which makes sense, right? If there's only one structure here, this is a photon interacting with a charged particle, it's the charge. What else could it be? Exactly, must be a little careful. It is the charge exactly, actually physical charge, if the momentum of the photon goes to 0. The photon or the electric charge is already defined with exchange with a 0 energy photon. That's when you get 1/137 for alpha electromagnetic. So this charge form factor when K, well, it's still called a charge form factor, but it's really the charge, the actual electrical charge, including all loops, etc., when K goes to 0. The Thomson limit is called. Okay, so we have that. Now we'd like to. I've only shown you what the charge is. Now I must show it's conserved. Okay, but so far so good. It's very general arguments. I haven't used operators, just diagrammatic insights. So now consider a process A goes to B plus gamma. So we'll see here, we'll discuss diagrams in a quite general sense, not diagram per diagram very specifically. We'll do that too later on, but very general sense. Now, A is some initial state, B is some final state, and one extra photon. I'm not more specific than that, so let me just draw blobs again. So we have here, say, 3 particles coming in. That's state A, and 4 going out. This is state A, this is state B. I'll copy it 2 times. 1, 2, 3, 4, 1, 2, 3, and again 1, 2, 3, 4, blob. 1, 2, 3. I will not draw the charge arrows anymore. So this is A goes to B, and the extra photon, these are all charged particles, can be emitted either, say, from one of the initial particles, or from one of the final particles, say here, or from somewhere inside. Those are the 3 logical options. Right? I will have reason to call the first 2 the Born, or it's a bit old-fashioned, I will call it perhaps also the iconal part, and this is the remainder. I'll have to explain that, of course. But to see how this now looks, having now understood that this particular coupling of the photon to the charged particle is proportional to the momentum, the sum of the two momenta, times the charge form factor, F1. That's the structure of my interaction. Now, there are two different ways of looking at it. So first we have here the process A goes to B, where one of the initial propagators has, so photon momentum K goes out, has an extra propagator here, because of the emission of the photon. Or one of the final state particles has an extra propagator, because of this bit. Or something else happens here, and I'll make that distinction with the first two in a moment. So let me write down the scattering amplitude for the Born process. And let me just build it up. So the very first thing we have, again here goes K. We have K going out, and we need for that such a polarization vector. So we have as first order of business to write down epsilon mu of K, and that will be contracted with the sum of all three types of contributions. Then we have here, I'll focus now first on this term, the scattering amplitude for A to B. I'll put a little I here, I'll explain in a moment, to go to B, with multiply the following term, 2pi minus k mu fi of k squared divided by pi minus k squared plus m squared, and the sum over I. That's all the contributions from any of the initial state lines. Let me see if I can explain this formula. So the sum over I is the sum over all initial state lines. Right, it's 1, 2, 3 in this case. And the ith line is the one that emits the photon. Right. So for that line, we have momentum pi coming in, and here pi minus k. So this bit is just the part of the amplitude from here on onwards, just again from A to B, whose only change is that instead of pi coming in, now pi minus k comes in. So that's why there's a little I here. Just a reminder, remember, it's the same amplitude as before, as if you didn't have an emission, except the ith line has a little less momentum. K is gone. And this bit is the propagator, this extra propagator. The sum of the two momenta, pi plus pi minus k, gives you this, divided by pi minus k squared plus m squared, times the charge form factor for that line. All right? So that's a functional way of writing it. And there's also a similar expression for the final states, which I will not have to explain. It just goes exactly the same way. Fj of k squared divided by bj plus k squared plus m squared times ma goes to b. What should I write here? Just to remind ourselves that now the jth outgoing line has a bit of extra momentum. Just write a little j index here. Right? And the whole thing must still be, bracket must be closed. So is this clear? So this momentum pi coming in, then pi minus k goes on, so that's why we have 2 pi minus k here. Now notice, suppose now I would like to, I'll discuss the remainder in just a second. One thing I'd like to do is go to the k to 0 limit. That's where I really understand. Then the form factor corresponds to the electrical charge. So let's consider I'll just do it first in words and then I'll write something on the board. Let's consider k slowly going to 0, to very small values. The first thing you can see is I can drop this k here, and also the k there. Now what does the denominator start looking? Can someone already see immediately what the denominator here becomes? remember p squared is on shell, so we have this. Sorry? It's not exactly 0, it's 2pi dot k, minus 2pi dot k. Right? Because the p squared term and the m squared term cancel, and k squared goes faster to 0 than 2pi dot k. So this thing goes like becomes 2pi dot k when k becomes very small. So you see here then, if we also ignore this, then we have pi over 2pi dot k when k goes to small. This is a singular term. When k goes to 0, this prefactor starts blowing up for the initial state, and very similar for the final state. And that is really because it's emitted from an on-shell line. That immediately explains why the remainder does not contribute, because this will couple deep inside here to some kind of off-shell photon. It will not become 0 when k goes to 0. It's far off the mass shell there, so the remainder term is non-singular when k goes to 0. Right?